Dear friends, welcome to this lecture of inner product spaces. In this lecture, we shall study theorem number 2, which is known as Gram-Schmidt Orthogonalization Process. That means given a basis, which means the basis contains linearly independent vectors and the basis spans the whole vector space V. But we shall form a basis which contains orthonormal sets as its vectors. So, orthonormal set will be a basis, and from the general basis, given any basis, we shall construct a basis which contains orthonormal set, and therefore this procedure is known as orthogonalization process. Now, for example, we will see if V is F3, three-dimensional vector space. Here we have to consider finite dimensional inner product space, and in this this is a basis. Say we shall consider, say, S. S is the vectors 1 0 0, then 1 1 0 and 1 1 1. This is a basis, but these vectors, so we may suppose this as V1, V2 and V3. These are the vectors. Then but these are linearly independent. The meaning of basis is these are linearly independent, and L of S is equal to whole of V, the vector space F3. Any vector in V, three-dimensional vector space, it can be expressed as linear combination of V1, V2, V3. That means linear span of this S is equal to V. That is the meaning of basis. Only we want to consider these, we want to construct a basis which contains orthonormal sets. These sets are linearly independent but not orthonormal, and we have proved a lemma: orthonormal sets are linearly independent. So, but this we have to consider orthonormal means they have the unit length and they are pairwise orthogonal. So, that condition must be satisfied. Now, we shall consider if this basis as 1 0 0, then 0 1 0 and then 0 0 1. Then here the vectors in this basis are linearly independent as well as orthonormal, and we will denote this by W1, W2, W3. That means from this basis S, we want to construct basis S1. Here these vectors are independent necessarily, but these are not orthonormal, and here these are linearly independent as well as orthonormal. So, what is the meaning of orthonormal? Each is of unit length. See, this is equivalent to the unit vectors ijk in three-dimensional space. 1 0 0, then its length is 1. Length of this vector is also 1, length of this vector is also 1, and they are mutually orthogonal. That means the inner product of W1, W2 is 0, W2, W3 is 0 and W1, W3 is 0, and the inner product with itself is 1. So, this is orthonormal. This set is orthonormal, but this is not, and thus we have to construct from this given basis a basis which is orthonormal. That is the meaning of this Gram-Schmidt orthogonalization process. Now, we shall start the proof. So, let V be finite dimensional inner product space, and V has orthonormal set as basis. So, this V has this orthonormal set as basis. Here we have, and this is done for every finite dimensional basis or finite dimensional vector space. It is also true for infinite dimensional, but we are considering only finite dimensional inner product space. Now, we shall start the proof. Let V be of dimension n. Let V be inner product space of dimension n. V be of dimension n. Then its if it is of dimension n, its basis will contain n linearly independent vectors, and this is three-dimensional, so it will contain 3 linearly independent vectors which span V. So, let V1 we denote V1, V2, Vn be a basis of n, basis of V, be a basis of the vector space V. From this basis we shall construct another basis which contains also n number of elements. We know that any two bases of a vector space of dimension n must contain n vectors which are linearly independent. So, from this basis we will construct other basis. So, here both S and S1 are basis of F3, and here also we shall construct from this basis we shall construct another basis containing n elements. N elements which are orthonormal, containing n elements, and this set is orthonormal. We shall construct another set and this set is orthonormal. And earlier we have proved lemma number 4 that orthonormal set is always linearly independent by lemma 4. This set, the set of orthonormal vectors, is linearly independent and thus forms a basis. This is linearly independent. And thus is a basis of V. So, this is the procedure that we will do in the proof of this theorem. So, what this is the given basis. From this we convert these vectors into orthonormal vectors, and again this orthonormal vectors and the n number of vectors, they will be linearly independent and they will form the basis required. So, we do the constructions as follows. As follows, we will form a vector, the set consisting of vectors w1, w2, etc., wn. We construct a set of n vectors w1, w2 and so on up to w1 n, each vectors of which each of these vectors has length 1. Each of these vector has length 1, means each wi has length 1, and inner product of wi with wj is equal to 0 for if I is not equal to j. So, this is the condition for orthonormality, orthonormal set. If this set must be orthonormal, and then when we say this set is orthonormal, each vector of this set has unit length, and the inner product of different vectors pairwise is equal to 0. So, this is what we want to construct. Now, in this we finally express w in this form. we express these vectors as W1. W1 is a multiple of V1, scalar multiple of V1. W2 is in the linear span. W1 is a linear span, is in the linear span of W1 and V2. W3 is in the linear span of W3 is in the linear span of W1, W2 and V3. And in general, now you see we are writing what is the procedure, how to express these vectors. We want this basis. From this basis, given basis, we want this one, and that means we have to obtain the vectors W1, W2 and so on up to Wn. And the procedure, we are having this condition, length of each vector is 1 and they are pairwise orthogonal if I is not equal to j. So this is we express W in this part. W1 is multiple of V1, W2 is in the linear span of W1 and V2, means W2 is combination of W1 and V2. Similarly, W3 is a linear span of W1, W2 and V3 means it is the combination of W1, W2 and linear combination of W1, W2, V3. And in general, Wi is in the linear span of starting with W1, W2 and so on up to, now you can observe W3 is the linear span of W1, W2 and V3. So one less number suffix is there. So for Wi, for W2 also it is W1 and V2, and so therefore Wi will be in the linear span of W1, W2 up to Wi minus 1, one less, you see, W3, W1, W2 and V3, and here, and this will be Vi. Vi is the last vector in this span. So Wi is in the linear span of this. Now we follow this procedure. Let first let W1 is equal to, what we have written, W1 is multiple of V1 and we shall take that as V1 divided by norm of V1. This is our first value of W1, and we shall check this is this must be orthonormal, and that it is single vector, so we have to check only its length is 1. So these vectors has each of these vectors has length 1, means W1 has length 1. And so now what is how to check the length, means norm we have to find out, and norm, to find norm we have to take the inner product of the vector with itself. So now the inner product of W1 with itself is inner product of V1 divided by norm V1 with itself, because W1 we have considered as this one, and this is equal to, these are scalars and positive, therefore we can write it outside by linearity property, and that will be norm V1 square, and in the inner product remains of V1 with V1, but inner product of V1 with V1 is again norm V1 square, and therefore this is 1 upon norm V1 square into norm V1 square, and the left side is also norm of W1 square, and thus the right side becomes 1, or therefore norm of W1 is equal to 1, norm square is 1, or that means norm is also 1, norm of W1 is equal to 1, and thus this vector is of length 1. So that condition is satisfied. Now we shall have to consider W2. So W2 we shall find out. Now we shall find out alpha. Now or next we shall find alpha such that, see, we want to now construct W2. What is W2? W2 is in the linear span of W1 and V2. So this procedure also we have to note how to express W1, W2, W3, etc. And according to that we are constructing these vectors. So we have to find out W2 in the linear span of W1 and V2. So therefore we shall consider alpha such that it is a combination of this W1 and W2, that such that alpha W1, the combination with alpha W1, but we shall take V2 as 1 into V2 plus V2 is orthogonal to W1. So because these must be orthogonal, the vectors, different vectors, so we are taking this as W2 and this W2 must be orthogonal to W1. If I is not equal to j, orthogonal means their inner product is 0. So therefore, this is orthogonal means alpha W1, the inner product of this alpha W1 plus V2 with W1 is equal to 0. That is the meaning of orthogonal, and this implies, see, by linearity property, alpha inner product of W1 with W1 plus inner product of V2 with W1, and that is equal to 0. We have expressed this using linearity property. But what is the length? This is the inner product of W1 with W1. Here we have, this is 1, this is the same, and it is 1. So therefore this is 1 means this implies alpha into 1 plus inner product of V2 with W1 is equal to 0, and this implies alpha is equal to, see, this implies alpha is equal to, we shift this term on that right side, and that is inner product of V2 with W1. So this is the value of alpha. Now we use this value of alpha in this combination and we take this as W2, because W2 is linear span of W1 and V2. So we take this as U2. Instead of W2 we first take it as U2. Now take or let U2 is equal to, let U2 is equal to alpha W1 plus V2. We are purposely denoting this as U2, not U1. V1, V2 are the basis that we have written. Now we are taking the vectors in the form of U notation. This is taken as U2, not U1, because this is to be considered for W2. And we let U2 is this, and therefore what is the expression for U2? This will be, therefore U2 is, this is alpha is this much, that is minus inner product of V2 with W1 into W1, putting the value of alpha here, plus V2. So this is U2. Now we shall claim that this U2 is orthogonal to W1 and W2. This U2, then U2 is orthogonal to W1. So this is easy to verify, that is since or for what is the inner product of U2 with W1. If it is 0, then these are orthogonal. We shall show this, or it actually follows directly by lemma number 5. So what is the inner product of this U2 with W1? We will write it directly, that is minus, we have to take the inner product of this is a scalar. So inner product of V2 into V2 and W1 into inner product of W1 with W1, taking inner product of this with W1. So it is inner product of W1 with W1 plus V2, I shall write here, plus V2, or here I can write V2, inner product of V2 with W1. So taking inner product of this with W1, the right side becomes like this, and we have inner product of W1 with W1 is 1. So therefore this is minus V2 inner product of V2 and W1 plus inner product of V2 and W1, and therefore it becomes 0. So this is equal to 0, and thus U2 is orthogonal to W1. Further, W1 since V1 and V2 are linearly independent, because this is a basis we have considered, V1, V2, Vn are basis, and the elements in the basis are linearly independent. Since V1, V2 are linearly independent, we have W1 and W2 are also linearly independent. So V1, why it will be linearly independent, because V1 we have considered as V1 is W1 we have considered. W1 is considered as V1 divided by norm of V1. So it is scalar multiple of V1, and V2 is linearly independent. So therefore we will say that this W1, W2 will also be linearly independent. But before that we have to construct earlier that that is W2. We have not stated again W2. So here U2 is this these orthogonal, and therefore W1 and W2 must also be linearly independent. But W2 we have not yet considered. So V1, V2 are linearly independent. We will say that this W1 and W2 are linearly independent. So U2 is a linear combination. It's a linear combination of W1 and V2. So because these are linearly independent, since we have W1 and V2, W1, V2 are linearly independent. See what changes we have done. These are linearly independent because of they are the elements in the basis, and we have changed only V1 as W1. What is W1? W1 is a scalar multiple of V1 that we have, V1 divided by norm of V1, and therefore this is this set is also linearly independent. And because this is linearly independent, so W1 and V2 appear in combination of U2. So these are linearly independent, therefore U2 must not be 0. This implies, so this implies U2 is not equal to 0. So why U2 is not equal to 0? If U2 becomes 0, if this is 0, see, if we assume if it is it were 0, then W1 and W2 are linearly independent. These are linearly independent, and by definition of linearly independent, this must imply their scalar multiples must each be 0. That is, alpha is 0 and 1 is 0, but 1 cannot be 0, and therefore this must not be 0. U2 must not be 0. So because these two are linearly independent, W1 and V2 are linearly independent, and the multiple of V2 is 1, so 1 cannot be 0. So therefore U2 is not equal to 0. And now we take W2 as U2 divided by norm of U2. We take W2 now as U2 divided by norm of U2. And now we shall claim that this W1, W2 is orthonormal set. Then the set W1, W2 is orthonormal. Is orthonormal set. So we shall verify this, since or for the reason for this, for norm of W1 is equal to norm of W2 is equal to 1, as earlier. If you take the inner product of W with W2, then it is 1. We have seen earlier, inner product of W1 and W1 with W1 is 0, is 1, and therefore both these are of length 1, and their inner product of these two vectors we shall show it must be 0, and inner product of W1 with W2. See, this is equal to inner product of W1 with what is the value of W2 is U2 divided by norm U2. And you see, this is this can be written outside, that is a scalar positive norm U2, and what remains in inner product of W1 and U2. And we have written here, or we have obtained actually here, inner product of U2 and W1 is 0, and therefore this is 0, or it can be interchanged by the first property, conjugate of 0 is again 0, and therefore this is equal to 0 by this result, and thus this satisfies the condition of orthonormality of this set, each of length 1, and they are, if their suffixes are different, then the inner product is 0. So that is the reason for this. Further, we shall consider now that U3. Now further let U3 is. Now how to consider U3, that we shall see. Earlier what we have considered U2 we have written as U2 is equal to, say, that is minus V2 comma the inner product of V2 and W1 plus V2. This is the expression for U2. Likewise, extending this, we shall consider U3 as U3 is equal to, or I shall write here, U3 is equal to, that is minus inner product of V3 with W1 minus inner product of V3 with W2 multiplied by W1, see like this, minus inner product of V3 with W2 multiplied by W2 plus V3. See how it is extended. This is U2, negative inner product of V2 with W1 multiplied by W1 plus V2, only one term. Here for U3 there will be two terms, starting with W1 inner product with W1, next we have to take its V3 inner product with W2 multiplied by W2, and the last vector is addition plus V3. So this is V3 that we should consider. Now this U3 is orthogonal to W1 and W2. Then U3 is orthogonal to W1 and W2, orthogonal to both W1 and W2. For we can first consider the inner product of U3 with W1. So you see this vector, and we will write that inner product directly on the right side. Take the inner product of both sides with W1. So this is a scalar quantity and it will remain the same, minus inner product of V3 with W1, then inner product of W1 with W1 minus again this is minus this is scalar, and inner product of W2 with W2 plus inner product of V3 with W1. And you see here this value is 1, inner product of it is orthonormal vector, it is its value length is 1, vector in orthonormal set, and therefore its value is 1, and this is W2 with W1, this is we are taking with W1, and here their suffixes are different, so this is 0, and see this is negative and this is positive, this value is 1, so therefore this becomes 0. Verify this, this is 1 and this is 0. So therefore U3 is orthogonal with the W1, U3 is orthogonal to W1, and similarly we can show U3 is orthogonal to W2. Similarly, inner product of u3 with w2 is equal to 0. So thus we have shown that u3 is orthogonal to w1 and w2. Now we will have here w1 w2 are in the linear span. Now w1 w2 and v3 are in the linear span, or these are linearly independent, since v1 v2 v3 are linearly independent, or we write this as linearly. Since v1 v2 and v3 are linearly independent. Because these are the elements in the basis, they are linearly independent, and w1 is a combination of that is a multiple of v1, w2 is a combination of v2. So we have expressed w2 earlier, and that is a combination of v2 in the form of v2 and v1, that is w2. So therefore these vectors and v3 is the same. So these are also linearly independent, and because these are linearly independent, see the vectors here in this combination, w1 w2 v3 are linearly independent, and therefore their combination must not be equal to 0. If their combination is equal to 0, then each must be 0, but last scalar is 1 cannot be 0, and thus this combination must not be 0, and thus this implies, and thus u3 is not equal to 0. So every time we are proving these vectors u2 is not equal to 0, now here u3 is not equal to 0. Now we will take the vector w3. So take w3 as u3 divided by norm of u3. First we have taken w1 as v1 divided by norm of v1, w2 as u2 divided by norm u2, and now we have taken w3 is equal to u3 divided by norm of u3. Then the set w1 w2 w3 is orthonormal. Is orthonormal set. And thus we are constructing the vectors like this. Every time we are getting one more vector and the set becomes orthonormal set. Now we proceed in the same manner. We proceed like this. And we will obtain, suppose we obtain the vectors w1 w2 up to wi, and if w1 w2 up to wi is orthonormal set, how to find wi plus 1? Then next vector, after three vectors we have obtained, then we have to find out w4, and in general if this is orthonormal set, then to find wi plus 1 we shall take ui plus 1. Ui plus 1 is equal to, now see, we have taken earlier u3, and likewise we can consider this ui plus 1 as minus vi plus 1 inner product with w1 multiplied by w1 minus vi plus 1 inner product of this with w2 multiplied by w2 and so on, and see the last but one term will be inner product of vi plus 1 with wi multiplied by wi, and last one will be v plus vi plus 1. So, this is the form of ui plus 1. Earlier we have expressed u3 like this, u3 as minus v3 inner product with w1 multiplied by w1 minus v3 inner product with w2 multiplied by w2 plus v3. So, this is extended here. You see the suffixes here, it is I plus 1, the suffix of v is I plus 1 in each inner product, and last but one term is up to I. Here is I plus 1, it is up to I, and last is positive vi plus 1. So, this is the expression for ui plus 1. And then the vectors here, the vectors w1, w2, wi are linearly independent and orthonormal set, and therefore these vectors w1, w2, wi and vi plus 1 are linearly independent. The set, the vectors here ui plus 1 is, and this ui plus 1 is orthogonal to each vectors w1 up to w1. Then ui plus 1 is orthogonal each of w1, w2 up to wi. So, this is the relation that we will have, and further, since w1 and up to vi plus 1 are linearly independent, also w1, w2 up to wi and vi plus 1 are linearly independent. As earlier, because if they are linearly independent, if they are linearly independent, their combination must not be equal to 0. If the combination is 0, then each scalar will become 0. Here the scalar is 1 and that cannot be 0. So, these are linearly independent we have. See, we have, I shall write here, we have this vector is not equal to 0. This vector ui plus 1 is not equal to 0. Every time we are writing like this, u2 is not equal to 0, u3 is not equal to 0, u4 will not be equal to 0, and in general ui plus 1 is not equal to 0. And why this is this must not be 0? Because we are considering, now take wi plus 1. How to take the next vector from this step that we are writing? We take wi plus 1 as ui plus 1 divided by norm of ui plus 1, and if this vector is 0, this will not be defined, denominator becomes 0. So, therefore, every time we are considering, or we are checking, or we are verifying that this is not equal to 0. Why this is not equal to 0? Because the right side vectors are linearly independent, and thus this is the next vector in the procedure to obtain n vectors. So, we proceed like this. Then, so thus in this way we from n linearly independent vectors, from the n linearly independent vectors in the basis, vectors which are the n linearly independent vectors v1 up to vn, we obtain the set of n orthonormal vectors. Set of n orthonormal vectors which are w1, w2 up to wn. or W1 up to Wn. And this is the required basis, which is the basis of the vector space V. Which gives the required basis. Basis of the inner product space V. So, thus this is known as Gram-Schmidt orthogonalization procedure. So, we have obtained W1 as V1 divided by norm V1, W2 as U2 divided by norm U2, W3 as U3 divided by norm U3, and in general Wi plus 1 as Ui plus 1 divided by norm Ui plus 1, and every time the set remains as orthonormal set. So, these are linearly independent, and these are orthonormal, and also they span the whole vector space V, and therefore, given a vector space V, which is a inner product space V, which is finite, then this vector space V has, or inner product space V has, orthonormal set as basis, and this is the orthonormal set, a set containing n orthonormal vectors. N vectors are containing n vectors in this set, which forms a basis of V. So, this proves the theorem, or this completes the proof. So, you go through the proof and try to understand this, which is known as Gram-Schmidt orthogonalization process. Now, the illustration of this actual how the construction is made with the with the help of an example, we shall consider in our next lecture. Thank you for watching the lecture.